So hello, everyone. Thank you for attending my presentation. I have a PhD in biomedical informatics, but my primary experience has been over the past 20 years in information technology in the clinical research area. In today's presentation, first I'm going to discuss the concepts of AI and deep learning. Next, I will discuss my dkNET project and how I'm building an AI framework that aims to predict T1D. The important features found through this AI framework will require discussion and validation by the TEDdy researchers, as they're the experts of the data and T1D and can provide valuable insights into the outcomes and features of this project. So artificial intelligence. Do you know you're using AI right now on Zoom? So Zoom uses AI to optimize connections, video compression, and audio transfer. And while there's no universally agreed on definition for AI, the term broadly refers to computing technologies that can perform tasks which normally require human intelligence, such as visual perception, speech recognition, decision-making, and translation between languages. Now, in medical research, AI is most commonly employed to analyze and identify patterns in large, complex data sets. Using AI, data may be analyzed in a significantly faster, precise, and more cost-effective way than traditional analytical methods. And during this research for this project, I found some really interesting technologies that are applying AI. One of those I found is at the Institute of Cancer Research in the UK. So for example, they have developed this unique, it's called CANSAR, C-A-N-S-A-R database, that's capable of combining patients' clinical and genetic data with independent chemistry, biology, patient disease information. And once this AI system has collated this vast amount of data into a common language, it can then employ these AI algorithms to make useful cancer drug discovery predictions. I thought that was a really interesting tool, and I'll cover a few others that I've found out about during this project and my research. So the concept of AI has actually been around since 1943, when Warren McCulloch and Walter Pitts, they wrote a paper on how neurons might work. And they made a simple neural network model with electrical circuits. But as you see on this diagram, machine learning didn't start taking off until about the 1980s. And it wasn't until about the 2010s when deep learning started to become mainstream. And a lot of people think that that's because of Moore's law, where the doubling of computational power every few years while the costs have been reduced. So like right now, I can run AI on my laptop, where 20 years ago, that was probably impossible. You needed a supercomputer. But since the computing power has increased drastically, AI has taken off. AI is being run on your phones now, where 20 years ago, that would be unheard of. So AI learning approaches. So there's three related concepts, and perhaps the easiest way to think about AI, machine learning, and deep learning is to think of them like a Russian nested doll. So essentially each component is of the prior term. So machine learning is a subset of artificial intelligence, and then deep learning is a subset of machine learning, and then even further than that, more granular, are the neural networks within deep learning. There we go. So deep learning model types. There are a lot of models to choose from, and it really depends on the problem that you're trying to solve and which approach you would like to take. There's models that are for temporal time series data. There's models that are really good for computer vision, natural language processing, video compression. So it really depends on like I said, what your goal is and what the project is. So for this project, I actually have temporal and static data. So I used a combination of LSTMs and multi-layer perceptrons, the MLPs. And just recently, over the past week or two, I've introduced autoencoders into the LSTM portion of my model, and I will cover that later. So there's a lot that goes into deep learning. It's a subset of machine learning. It utilizes a hierarchical level of artificial neural networks to carry out the process of machine learning. The artificial neural networks are built like the human brain, with neuron nodes connecting together like a web. Now, while traditional programs build analysis with data in a linear way, the hierarchical function of deep learning systems enables machines to process data with a nonlinear approach. So as you notice in this diagram, first we have inputs, and the inputs to a neuron can either be features from a training set or outputs from a previous layer's neurons. So this can either be the starting point of your model, or it can be in the middle, or each layer. They're going to receive inputs and continuously go back and forth. Then you have the weights. So the weights are applied to the inputs as they travel along the synapses to reach the neuron. And when the inputs are transmitted between neurons, the weights are applied to the inputs along with an additional value, which is the bias. And then within the neurons, the heart of it is the activation functions. The neuron then applies activation functions to the sum of the weighted inputs. So for each of these incoming and synapses and passes, the result is passed on to all the neurons in the next layer. And activation functions give neural networks their real power, as they allow them to model complex nonlinear relationships. By modifying the inputs with nonlinear functions, neural networks can model highly complex relationships between features. And this is truly an added benefit between deep learning and probably the normal analysis approaches. And some of the popular activation functions include ReLO and sigmoid, and there are constantly new ones that are proven to be potentially better given the situation, because not all of your layers will be beneficial depending on the activation function. So for instance, maybe you have an activation function that may not work well with a convolutional neural network, but it works well with LSTM or your data. And then these synapses that you see that go between the inputs to the neurons and then the neurons to the outputs, they're like roads in the neural network. So they connect the input to the neurons to neurons, and the neurons to the outputs. So in order to get from one neuron to another, you have to travel along this road, this synapse. And along that route, you're paying a toll, which is the weight that's applied. So each connection between two neurons has unique synapse with unique weight attached to it. And when we talk about updating the weights in a network, we're really talking about adjusting the weights along these synapses. And the deep learning is composed of several layers. So your first layer is your input layer, which holds the data of your model that you train on. And each neuron in the input layer represents a unique attribute in your data set. That could be something simple as height, hair color, eye color, or even more complex, getting into genome sequencing or microbiome data, proteomics data that I'm using in this model. And then you also have, after the input, you have the hidden layers. So they sit between the input and the output layers, and they apply an activation function before passing on the results. There's often multiple hidden layers in the network. And in traditional networks, hidden layers are truly fully connected layers where each neuron receives input from all the previous layers' neurons and sends its output to every neuron in the next layer. And this contrasts with how convolutional layers work, where the neurons send their output to only some of the neurons in the next layer. And then finally, you have your output layer. This is the final layer in the network. You receive input from the previous hidden layer, optionally applies an activation function, and returns an output representing your model's prediction. So in my case, this would be a binary output, and it would be either 1 or 0, and whether this person was either IA positive, negative, or T1D positive or negative. And then another important aspect are the loss functions. So a loss function, it's also called a cost function. It's like a wrapper around the model's predict function that tells you how good the model is doing. And it's how good it's at making predictions for a given set of parameters. The loss function has its own curve and its own derivatives. The slope of this curve tells us how to change our parameters to make the model more accurate. We use the model to make predictions, and we use the cost function to update our parameters. Our cost function can take a variety of forms, as there are many different cost functions available. Some of the popular loss functions include like MSE, L2, cross entropy loss, and a variety of others. And I'll discuss that a little further because you can see the framework that it develops uses TensorFlow, and it outputs nice curves so you can see your loss and look if the data is being underfit or overfit. So training the neural network It's an iterative process, and it uses optimization techniques like gradient descent. So after each cycle of training, an error metric is calculated based on the difference between prediction and target. The derivatives of this error metric are calculated and propagated back through the network using a technique called backpropagation. So each neuron's coefficients, essentially their weights, are then adjusted relative to how much they contributed to the total error. So this process is repeated in an iterative fashion. So there's a lot in that slide. So next, in deep learning neural networks, each layer of nodes trains on a distinct set of features based on the previous layer's output. The further you advance into the neural net, the more complex the features your nodes can recognize, since they aggregate and recombine features from the previous layer. Now, this is similar to how your brain works and why I think this is all like neural networking. So think of when you want to solve a puzzle, you have all the pieces, these features of the puzzle. What do you first just start with edges, things that you may not recognize as part of the puzzle. Then you slowly add them together and eventually, hopefully you solve the puzzle. And that's similar to maybe when you hear a plane in the sky and how your brain starts to have certain features that are associated with the plane, like maybe your sound, the visual. You may look up, try to find it. You see a bird, but how do you know that's a bird, not a plane? You recognize things like, oh, a bird has feathers, a plane doesn't have feathers, a plane has the vapor trail behind it, a bird doesn't. So there's things and features that your brain associates with a plane. And that's similar to how deep learning works with applying it to data. It looks for these patterns that eventually lead to the output. In my case, it's binary, but it could be non-binary and classifications on other things. Primarily, I think a few presentations back, AI is being used to determine the size of pancreas. And you'll see AI is being heavily used in vision and video. It's used on cars for autonomous driving. So during my project, I found a lot of interesting applications where AI is being used to successfully predict a lot of health-related predictions. Some interesting ones that were similar and gave me some insight and inspiration on this project were some Alzheimer's diseases. There are Alzheimer's diseases based on, the prediction is based on a bidirectional LSTM. And then there's also AI that's been able to predict progression of diabetic kidney disease. And Google, who develops like TensorFlow, they have a really good AI department. They've developed this DeepMind tool that predicts the likelihood of a patient developing acute kidney injury, AKI, which is a life-threatening condition. There's a lot of tools out there, especially the last, I'd say, five years that have been developed, especially in the healthcare area. That's vastly improved not only the knowledge base of healthcare, but individuals who are interested in AI development, specifically in clinical research. One interesting AI project that I found was researchers at MIT and Harvard. They're using AI to detect skin cancer, and it was able to successfully distinguish these lesions that are serious from patients that, or from lesions that are not serious with 90% accuracy. Now that's great. Now, does it replace a doctor? No, but what it can do is allow them to be more efficient. Take a picture, could even do it at home, send a picture to the doctor, run it to the AI, and then maybe you get if you get an accuracy of 90%, it's like, oh, you need a visit. Maybe not, but it's definitely streamlining a lot of the healthcare procedures. And it's very interesting to see how it works. I also found some that work online with your phone. So you could take a picture, say you have a mole that you're worried about, you take a picture of it, you send it in, it's processed in their cloud, and then it'll report back whether it's benign or malignant, and it gives the accuracy predictions outputted from the AI model. And I believe it had the sensitivity and specificity as well with that. So now that I've covered some AI concepts, I'm going to discuss my project with dkNET. So the goal of my project is to use AI and machine learning tools to develop a novel computational approach for synthesis and analysis of multi-omics, clinical and environmental data to evaluate the prediction of type 1 diabetes. Along that, I'm going to develop a framework that's used in pipelines for the fusion analysis of multi-level and multi-scale data. So I'm hoping to make this more broad, so it's not just applying it to type 1 diabetes. There's a lot of tools that I'll discuss further that I think I can package and put out on GitHub that could be used by others to help with their AI analysis. And also this AI is capable of learning temporal and static data. And while this exploratory study has limitations, the approach taken to identify possible T1D predictors may further advance the understanding of type 1 diabetes. Some underlying assumptions of this project is that the results may not be applied to the general T1D population. It's also using TEDdy data. It's TEDdy study, which I'll cover a little bit, as an NIDDK funded study. And I'm using the nested case control study population. And I'm going to examine the TEDdy T1D in persistent and confirmed multiple autoantibody IA diagnosed patient populations of the nested case control cohort. Now, I know the TEDdy researchers are currently in the progress of creating the nested case control 2 study, and that will have even more patient population, so the statistical power will be higher in that one. But at this time for my project, only the NCC1 data are available. And also that quality control metrics, background correction, and data normalization are performed on applicable data prior to analysis. As I mentioned, the data is from the NIDDK funded study, the Environmental Determinants of Diabetes in the Young, otherwise known as TEDdy. So the TEDdy study is designed as a prospective cohort study of approximately 8,677 children who were enrolled before 4.5 months of age, and they were followed for 15 years to identify genetic and environmental triggers of type 1 diabetes. The TEDdy cohort consists of children identified to be increased genetical risk, the HLA, DR, DQ genotypes, who either had a parent or sibling with T1D, first degree relative, or not, just the general population. TEDdy planned analyses include the comparison of natural history and biomarkers of those children developing T1D to those who do not. So the TEDdy study investigators are going to investigate genetic environmental interactions, including gestational infection or other gestational events, childhood infections or other environmental factors after birth in relation to the development of prediabetes, autoimmunity, and T1D. And TEDdy is a multinational study, and the long-term goal of the TEDdy study is the identification of factors which trigger T1D in genetically susceptible individuals, or which protect against the disease. So which is really interesting for me, and which I hope maybe we could provide more insight with my project, is the important features that we may find to predict IA positivity or negativity, or T1D positivity or negativity. We can look at these features and how they're weighted on the model to see if they're weighted heavier towards the progression of T1D or as a protective. But since I'm not an immunologist or endocrinologist, I would definitely need the TEDdy researchers and the TEDdy DCC to help me out and understand that data even more, and how it may lead to the pathogenesis or protection of T1D. The TEDdy participants are followed for 15 years for the appearance of various beta cell autoantibodies and diabetes, and they're no longer followed once they reach the study endpoint. And one of the study endpoints is the diagnosis of T1D. And so, as I stated, TEDdy is a multinational study that recruited participants in Europe and the US. The European sites are in Sweden, Finland, and Germany. We also have sites in Florida, Georgia, Colorado, and Washington. So TEDdy researchers have been finding a lot of information over the past, I'd say 10 to 15 years that the study has been going on. So one of the findings that I felt was very insightful for this project is that the TEDdy researchers have found that autoimmune destruction of insulin-producing cells typically begins in the first 2 years of life. So that was really interesting to me, and I felt that if this is happening within the first 2 years of life, that would be the really best data set to look at and analyze to try and predict T1D or IA positivity or negativity. Researchers have found that if there are multiple persistent confirmed autoantibodies, that they typically develop T1D within, I think, 70% within 10 years and almost 100% within 20 years. But that's multiple persistent confirmed autoantibodies. I think if they just have a single confirmed antibody, it's not as highly associated with T1D. And as type 1 diabetes is a complex autoimmune disease, resulting in destruction of beta cells, leading to deficient insulin production over time. Diabetes is a worldwide epidemic, including type 1 diabetes, type 2 diabetes, which is the most prevalent form of diabetes, and then also atypical forms of diabetes. And really interesting statistics that have been coming out is just the increase, especially in the younger population, from in 2001 to 2009, individuals younger than 20 years of age, it increased by 23%. And then the CDC's 2020 National Diabetes Statistics Report shows the prevalence of T1D in the US increased nearly 30% from 2017 to 2020. These are drastic increases. So this research towards type 1 diabetes, I think, is very, very needed in this, especially the States, but globally. And 3 different factors may contribute to the destruction of beta cells in the pancreas and lead to insulin deficiency. So they're environmental, genetic, and immunologic. Researchers think T1D is caused by genetic traits and environmental factors such as viruses, infections, and other exposures. Research has shown that the general population actually may have the same risk for developing T1D compared to the genetically at risk. So that'll be something I would have to talk with the TEDdy researchers on, whether I can apply this to the general public or only the genetically at risk. And there are at least 5 autoantibody reactivities that are predictive of T1D: ICA, IA, GATA, IA2A, and the zinc transporter. And the association between autoantibody prevalence and T1D confirms the importance of antibody detection in at-risk individuals prior to clinical onset. So my project, which is using AI to try and predict type 1 diabetes or IA positivity or negativity, is a data-driven AI approach that explores the TEDdy study data to predict T1D. And I'm hoping that it will provide valuable insights into the important features that may cause or protect against T1D. I use deep learning neural networks, recurrent neural networks, but I use a subset of that, the LSTM, long short-term memory network, multi-layer perceptrons, and I combine a combination of neural networks, so they're concatenated, which is a crucial feature of this framework. As this TEDdy study data has a lot of static data, family history, maternal history, SNPs, diet data, so there may be proteomic data that just says, yes, they've taken probiotics or prebiotics by a certain day, or just binary, yes or no. We also have a lot of dynamic and temporal features, such as the proteomic data, gene expression, RNA-seq, there's whole genome sequencing, test results, and other omics data that are available for us. Right now, the first iteration, I've been looking at proteomics in combination with SNPs and other static data there. I mean, the proteomic data is the temporal data. So what tools did I use for this model? It was programmed in Python version 3.7. Now these may change because some of these I need to update, but some I'm limited to. As you'll find with open source, you can't always upgrade to the latest version because some packages just aren't compatible yet, so you may break your code. So I plan to fork the code eventually and try to upgrade certain versions, but for now it's using Python version 3.7, TensorFlow version 2.5, and Keras version 2.3.1. I use Visual Studio IDE, but then when we want to deploy this to the HPC environments, we use SnakeMake, and GitHub is used for version control and source control, or source code management. As I mentioned, the data comes from the TEDdy study, and I limit it to the first 2 years of data from the TEDdy nested case control for the first iteration of this model. Now I can expand it, but as I mentioned, if an individual develops T1D, that's an endpoint, so we may not have data. So you also may have to impute a lot more there and risk some biases that are going to happen because you're either imputing or interpolating the time series data. The data that I'm using is temporal time series and also static. It's diverse. It has multi-omics and environmental factor measurements that happen every 3 to 6 months for 15 years. Now, I don't use the entire data sets. I'm not using 15 years. Like I said, I'm limiting it to the first 24 months or first 2 years for now on the first iteration of this project. So the AI workflow. So the framework consists of a lot of different tools, and I'll discuss some of these in more detail. But there's a lot of steps that are needed, as you can see, before you even make it to the AI model. And some of these are very critical and important to apply to the data before it's passed into the AI models, or else the model just won't work. So we start by acquiring the data, which could be static or temporal, and then we have to pre-process it. And when we acquire their data, these may be many, many, many data sets. So I rely heavily on the researchers and the data engineers that are at the Teddy DCC at the University of South Florida, because the data, even with data dictionaries, it's really complex and could be difficult to understand. There's so many variables that it could be a little confusing, and it was confusing to me, and I know the Teddy data well, but there's so many different variables, and when you're looking at the temporal data over time, it can even be more complex, especially when you add in the omics, which is very high dimensional, and you have so many columns or features of that data set. And then you're going to concatenate them, aggregate them. For Python, I use pandas to do a lot of the data masking, dropping, pre-processing steps. It's a really good library for that. The data imputation process is essential. You need to impute data. Not every data set is perfect. There are various options that you can do in this framework that I'll discuss later for that. And then also feature selection. So AIs are really great at predicting or modeling data, but they also have constraints. I mean, if there's so much data, there's limitations. So one option to do, if you notice that your data is either overfitting or underfitting, is feature selection. So you can narrow it down, so you're just passing it potentially the important features. But you can also pass it all the data and let the AI determine what are the important features of your data. Then to train it, you typically have to split it. And you'd split it into a training, validation, and test data set. Then you scale it. Then you actually have your AI model. Then the AI model has all of its outputs, which are critical for you to look at, because you would go back and tune the hyperparameters. And then one important area that a lot of individuals would criticize about AI is it was a black box. So it's like, okay, great, I made this prediction, but why did it make the prediction? So luckily, there are a lot of tools now that go into that black box, kind of unravel it, and let you see inside of the AI and show you the important features and all the measurements behind that went into that model's decision on why it made this output, which is key to continue with the research. I mean, it wouldn't be really important to me if it just made a great prediction of T1D, and then I didn't really know why. I mean, that's not really going to progress the science. So thankfully, there's a lot of nice tools that help with that, and they're incorporated into this model. So first, we have to acquire the data. And I loaded multiple various data sets for this, and they comprised of omics. The first iteration primarily had proteomics. I intend to add more data as we progress. And we also have environmental and exposure data that's static. And it's all from the nested case control version 1 study from the Teddy cohorts. Then we masked the data. So we essentially de-identify it. And I know there's data masking could be multiple things, but for this procedure, the data masking here is to de-identify or obfuscate the data. So we enhance the privacy, even if the Teddy data is pseudo-anonymized already, but it helps prevent potential research bias. So if I know that particular subject identifier and certain attributes, maybe I could have biases on that. That's an important step. And then data aggregation. here's where, and I used the pandas library in Python to do a lot of the data aggregation, pivoting, transforming, merging. We have these vast amounts of data sets available from the TEDdy study, which are great. It's probably one of the most richest type 1 diabetes data sets available. So I had a lot of help from Dr. Christian Lynch there and Chris Schaefer for helping me understand the data better, because it's, as I said, it's very complex, and I want to make sure I'm joining and merging these data sets correct. And then you have to transform these two-dimensional data sets, the ones that are temporal, into 3D time series structures to feed into your network. So data dropping. Now there's some elements that I dropped from the data. So some of the proteomics, for instance, may not meet the level of detection. So you can either choose to use that as a binary 1 or 0, or just drop it. I dropped the ones that were below the level of detection. There weren't many, but there was definitely some. Also censoring some data. So like I said, I only want the first 24 months. And then there's other data that may be dropped because they may hinder the model's predictive power, such as participant identifiers, viral barcode numbers, or dates of collection. Those are not essential for the model to do predictions. And it's just extra noise that you're adding into your model for the AI to run the neural networks. So imputation. Imputation is definitely critical in this, especially for the time series, which there's various methods that you can employ, especially in this framework. So you can do interpolation, you can do last observation carry forward, next observation carry back, case complete, but they all have their pros and cons. For this model, I used interpolation, and that's essential because not every participant goes think about it, they're expected to do these collections every 3 months. So that's hard for everyone to conform to that in a perfect world. So they're doing 3, 6 month, 9 month, 12 month, 15 month, and so on. So there may be plenty of patients maybe they have their 3, 6, 9, but they're missing their 12, but then they have their 15. So we do interpolation on that time series data for the imputation process. And the static data for this project, we chose to do the median, which is used by the AI model. Feature selection, as I mentioned, is really important if you want to reduce the number of input variables when you're doing your predictive AI model. So it could reduce your computational costs. If that's not an issue for you and you want to just run on HPC, then maybe you don't require feature selection. But it can also improve the performance of the model. So if you notice maybe you're not getting good accuracy, you just have too much noise, there's ways you can use feature selection to improve that. And there's various methods you can employ to do that: random forest, support vector machine, select k-best. They're all viable options, and you can choose which one you want to see which features you get back. And you can, with this model, like I said, choose any of those features, and in return, you pass it to N as well, or you just allow it to select that N for you with other procedures. A really critical part of the AI process before it even gets to the model is splitting your data properly. So what's nice is scikit-learn has a nice feature that will do a train test split function. So it'll split your data into sets, and you define how you want to do those splits. But for this project and many others, you don't want to just do your training and validation. You also have your testing on what you want to look at afterwards, after you train the model. So this data are split 3 times. So we first split it 10% for the training, then the remaining data are split 80-20. So 80 for the training, 20% for the validation, which are really critical for you to gauge the precision and performance of your model. And they also offer stratification procedures. So you can stratify by your Y value. So you ensure that your training and your test and your validation data sets all have comparable amounts of your Y values, or 0 or 1. So you don't have unbalanced data sets, because you could potentially, since this is randomized, and shuffled, you could have a test data set that has all zeros, or potentially the training data set has many more T1D individuals or IA positive individuals, so it's only learning that. So you really want to stratify and have a fairly balanced data set if you can. And then also data scaling. So prior to modeling the data, scaling and normalization are essential. And these indices are sensitive to dissimilarities in magnitude or scales of attributes. So the goal is to equalize the size, the magnitude, and the variability of the features. So you may have one feature where the range is exponential almost, and then the others could be 1 or 0. So scaling helps provide the model with a similar area of magnitude on that. So this model, I used robust scaling as it can accommodate data outliers. There's other scaling that are available in scikit-learn and other packages that simple imputation or simple scalars, but they aren't as great with outliers. So if you have outliers in your data, I would suggest using robust. And even if you don't have outliers, you can still use robust scaling. So as I mentioned, the TEDdy data used for this project comprises temporal and static data. So in order to predict IA and T1D outcomes, we developed a deep learning model that's capable of learning from temporal and time series. So it does concatenating of these neural networks. So within TEDdy, IA individuals have a single positive autoantibody. They're actually at low risk for progression to T1D, but individuals expressing 2 or more positive autoantibodies, especially on multiple tests over time, have nearly 100% risk of developing clinical T1D. And that was found by researchers that studied I believe it was TEDdy and TrialNet data, and which is critical to what I want to do. So first, I'm only applying this on the IA positive, because I assume that hopefully we could use that for the T1D, but also should be a good predictor of type 1 diabetes, even if it's just IA positivity with these multiple persistent and confirmed individuals. And then the future work would predict T1D if the IA positivity is determined that it's not a good indicator of T1D, but although I think it is, just given research findings from the TEDdy and TrialNet researchers. So the data outcome is binary, it's 0 or 1, which represents persistent and confirmed islet autoimmunity, IA. Then IA is determined, which is defined in the TEDdy study as using MIAA, GATA, and IA2A autoantibodies. And it's persistent and confirmed, so they have multiple positive tests. One area that is probably underestimated the complexity of is the AI hypertuning parameters. And there are many hypertuning parameters that are available that I'll cover next, but building AI models, it's iterative, and in order to optimize it and the model performance computing resources, you have a lot of these hyperparameters that require tuning. The settings are adjusted during each iteration, and it kind of governs your training process. And it also impacts your model metrics such as accuracy. And I'll go into what these are. So here's some examples of a lot of the hyperparameters that can be set. And you can also use tools that will try to tune them automatically for you. They may work, they may not. I found it's good to also write loops that'll change the parameters just so you can look at the output of your models to see what they're doing. The downside of this, I would say, with AI is it takes many hours to potentially run just one model. So if you don't have an HPC or run it locally, you may be waiting a few hours to get any results. So it's time consuming for that. But some of these parameters are like batch size, number of epochs, number of hidden layers, your dropout. Dropout is essential. If your model is overfitting, you can apply dropout to that, which there's the learning rates, optimizers, regulation, gradient clipping, activators, loss, cost functions. All these can be tuned. And like I said, there are tools that can help aid with that. For this model, we used a batch size of 32. You can reduce it and look at the output, but remember a smaller batch size. Remember, it's called like mini batching. It will actually, if you lower it, it could take longer to compute. So if you went down to, say, from 32 to 8, it would be a potentially slower process. So here's a general overview of concatenating a model. So it's, you have your RNN and MLP, they get concatenated, then you have your final output. Here's the actual output model of the one that we're using here. So we have our input layer, it's bidirectional LSTM. Just recently added autoencoders, so it's encoded, decoded, and then a part of that is the attention layer. So that's a newer thing people are applying, kind of like a transformer to autoencoders to improve that. We're using Gaussian dropout, then we flatten it because it's three-dimensional, and then we concatenate it with the static layers, and then we output. This is the binary output, 1 or 0. So the model is quite complicated, but I'd say the process in general, all the way up to the modeling, is a very complicated process. So, testing and validation are critical, and I found this out the hard way. So I started receiving really good prediction accuracy rates, that are above 90%. But my tuition was telling me, man, this seems too good to be true, because we had just proteomic data combining it with SNPs and other data. And, based on the TEDdy steering committee meetings, they really weren't sure that, just proteomics themselves would be able to predict type 1 diabetes. So we really sat down for a while to validate the model, to look at the code under a microscope, to make sure there wasn't an error in the code. We also found out from Dr. Owen McKinney at Cambridge that there's a tool called clairvoyance. That's an AI tool that is used to predict diseases. So I had an engineer, Leo, download that, and he ran that to try and compare our data, but he wasn't getting good accuracy results. I was like, well, either we're not understanding that tool or we're not understanding our model. I did end up finding it was our model that had a bug. So I modified that, but unfortunately the accuracies went down into, I think they were about 50s, 60s. We got it modified up to in the 70s, but unfortunately it was a drop. But now I feel like it's more realistic and a lot better that I found the bug now than later on when we're trying to do publications or anything more on this. So it was a critical bug that we found. Unfortunately, we found it, and it did lower the accuracies. So when you run the AI model, you see these nice graphs, and this is how you can see how well your model is performing. So the blue line is your training data, and the green, which is slower, is the validation data. Now you can sometimes determine if your model is under or overfitting just by the accuracy. Like if your validation is super high, your training's low, maybe underfitting. So there's hyperparameters that you can tune for that. And the same thing for the loss. This is the big one. A lot of models, especially if you're just doing with an RNN, because they have that vanish gradient problem, which are resolved by the LSTMs, which we're using here in this model, but they are susceptible to overfitting the data. And what you'll see is, if you're overfitting, this drop in your validation data may go down, and then it will drastically go up really quickly. So it's overfitting that data, and it's learning too much on the training data, which is not similar to your validation data potentially. So it's not learning the data correctly. So you can adjust different hyperparameters for that. And then another metric that's critical is to look at the precision. So you can determine what proportion of positive identifications are actually correct. And as you can see, this one, the precision is 0.78. We have your confusion matrix to look at the predicted labels, and you can see that predicted 25 IA positive correctly, but then 16 of those incorrectly. It predicted them as IA negative. And then you have your recall, your sensitivity, which is another good model. I mean, a lot of people will look at accuracy and loss, but precision and recall are very important metrics to look at as well. So here you can see the precision is quite low. So hopefully when we add more data, we can get this precision to go up higher. So it's, we have 25 true positives, but then, when you add the 25 and 16, you're actually getting a recall of 0.6. So not great, prefer to be close to 1, but like I said, we hopefully can add more data to the model. The area under the curve, right here, we're getting a 0.75, and the closer to 1, the better. So but these are all these graphs that are outputted by the model, which help you, and the numbers as well. So you don't have to just look at the plots. You can just look at the raw values as well if you don't want to plot your data, because that is time consuming as well. And then given the most AI models are stochastic in nature, building these models, it's an iterative process. So you don't want to just run it once and take that as, well, that's your accuracy or that's my loss, precision or recall. So what you want to do is repeat it and then look at your mean values and look at your standard deviations about that. So right now we're getting about, as for accuracy, 72% accuracy, which is good but not great. And the loss is really good. It's not overfitting the data. We're at 0.6. If you have a loss under 1, that's really good. So that tells me that maybe this is the highest we can actually predict given the data that we have, which is Olink, proteomic data in combination with SNPs, environmental and diet data. And we plan to add more data here that hopefully will provide more insights and then also improve the accuracy and the loss on these models, not the loss, but the accuracy and precision and recall. And then this is what really is important. This is kind of, I had to mask this, but each line here represents a feature and it's ordered by the most important feature of your model. So these are the top 10 temporal features of the model. So this is using the SHAP library. And what you can do is, it really helps you out. So say this up here is a cytokine. I don't know which one because it's masked, but so right now this would say that the high value of the cytokine would leads the model to predict IA positivity, where a low level will lead to IA negative prediction. So the next line would be a high value of this feature would lead towards a protectant or IA negativity, where a low value would lead toward the model to predict IA positivity, and so on. And these are ranked by importance. So, this is the highest ranking feature, then it goes down. And the same thing, so since we have one output, where we have two different inputs, the static and the temporal, you can also look at the important static features that impacted the model. So here you could see a high value of the value that was here, which is masked, led to a IA negative prediction, where a low value leads to a IA positive prediction. And now this is run on the aggregate of the test data. You can also look at how the training data, what the important features of that are, and then you can also run each individual participant in this model and see more like a precision medicine type of view, how that individual was chosen to be ranked IA positive or negative, and look at the features for that individual, because they may be a little different than the entire data set or the entire test data set, because everyone is a little different. And I really hope to gain more insight with more data. So what are the limitations of this project? It analyzes high dimensional clinical research data, and not all data were available at this time. Like I said, there's another nested case control study going on that I think would increase the data, which I think right now we had about 830 participants that are in the nested case control 1 that are in the 1-to-1. I think maybe a little below 830, but that's not a lot considering running things through deep learning. If we can get more than that, that would be great. As I said, the cases have nearly doubled, so we have more type 1 diabetes participants with this second case control study. And we also have limitation are the study endpoints. If the study participants who are diagnosed with T1D are no longer followed, so it limits the amount of data available. I think JDRF did sponsor the follow-up study with that, so some of those data points are, but there are a lot of missingness in the data points for these T1D participants once they've been diagnosed. Also, the important features must be validated and reviewed by the study researchers. Like I said, I'm not an immunologist or endocrinologist, and the TEDdy researchers at the DCC and all the clinical centers, the PIs, I mean, they're the ones that really know this data. So once we find these important features, it would be great for them to kind of dissect that and really understand how they may lead to the pathogenesis of T1D or act as a protectant against T1D. And also, it may be difficult to generalize these results to the T1D general population. And we did have to censor and impute, so there could be biases with the imputation or missing data. But what are the current outcomes? So I'm really proud that we developed this framework. I mean, it's still a work in progress, but it incorporates omics and environmental data. So it does the time series and it's doing static data as well. It now successfully transformed two-dimensional data to three-dimensional data to feed into these neural networks, which is critical. And TEDdy, they have do numbers, so it's a lot different than like predicting weather, which is a date and time. I mean, these are just do numbers 3, 6, 9. So those are transformed in a time series. It concatenates AI neural networks, LSTM and MLP. And currently, we're predicting on the test records about 83 test participants with a mean accuracy of 0.72, the IA positivity or negativity. And while the AI model still needs to be validated internally by the project team and TEDdy researchers, I feel like we've really successfully combined the omics and static data from the TEDdy study that can be run through this whole model. We have a lot of these packages that we can deploy. And hopefully we can provide the TEDdy study with valuable insights once this project is complete. And then not just that, but packages that can be used by other researchers out there that want to perform similar analyses, either on diabetes or other diseases. So what are the next steps? We need to enhance the current AI models. As you saw, the accuracy is it's in the 70s right now. Like I said before, I found the bug last week. It was higher, but intuition told us that maybe that was too good to be true. Right now, it's predicting IA positivity and negativity, but we eventually would hopefully be able to predict T1D. But IA positivity or negativity may be enough. We want to acquire and prepare additional data. I know that there's been like some immune responses from microbiome data that we could use. There's the gene expression, RNA-seq data that's available. So hopefully we can concatenate these data, temporal data into the model. Maybe we'll even provide more insights and get better predictions. So that's one big next step. And then obviously we need to quality control the entire framework and model to make sure that we do our internal construct validity, and then generalize the framework to incorporate additional methods and models to predict various diseases, and collaborate with TEDdy researchers to validate the model outcomes and important features. And I'd like to thank the Health Informatics Institute at USF, especially Dr. Jeffrey Prisher. He leads the DCC there for TEDdy, and Dr. Christian Lynch, who helped me really understand the data, along with Leo Moreno, who helped program this application, and Chris Schaefer, who helped me also understand the TEDdy data. As I said, it's very complex, and I think it's easy to misinterpret some of the data without someone very knowledgeable like that group. The TEDdy Publications Committee for reviewing all this for me, and also hopefully working with me to create an MP so we can publish a lot of these results. The entire TEDdy study group, NIH, NIDDK, all the clinical centers, investigators, and especially the participants for providing this data. And then also dkNET and NIDDK for sponsoring this project. Thank you.
Thank you, Ken. Great presentation. So now is our Q&A session. You can unmute yourself, or if there's multiple people want to ask questions, just raise your hand and I can call your name. And then you can also use the chat function. Okay, so there is one question from the chat from, I think it's Dr. Young. Is there a rule of thumb for the minimal sample size required, including training, validation, test sets, when the outcome is binary cross-section data? Are the numbers of predictors and the cases for binary outcome factors to consider for determining an appropriate sample size?
I don't think there's a minimum, but I mean, that is a good point, because neural networks, they really do like a vast amount of data. Right now, this temporal data, so if we have 800 participants, depending on the time point, so if you have, say, 24 time points, you divide that by 3, you're looking at, it's 800 times 8. So your data, your rows are much larger. So, but there are, I mean, I'd have to look at recommendations, but if you only had a small, like for rare diseases, it's actually a lot more complicated. But I know that there are applications out there that have used like LSTMs, and there's also new models that are being developed what are they? There's one that's called, I think the transformer, and that helps with smaller data sets, and it does like auto encoding, and then also the attention is used for that. So you can have like smaller data sets, especially for like a rare disease type application that you could apply neural networking towards.
Okay. And then I think there's a question from Ali Sina. You can unmute yourself.
Hi, this is actually a comment. You are concerned about the level of accuracy, performance of your results. I think one independent way to check it would be to request some medical people to look at the same data and come up with their conclusions. Because in some other instances, the conclusions of the medical expert was about 50–55%. And if you are doing 70 and theirs is 55–60, then your tool shows that it has value for the researchers, for the medical researchers.
Right. No, I completely agree. Yes. While 70% is not great, it may be better than, like you said, 50% in the medical industry. So I think it's definitely going to be a valuable tool. I do want to apply more data. I feel that there's other data, even if we just increase the accuracy a small percent, I think it'll provide more insight so we can look at potential cause and effect with maybe the immune response to the cytokines and how they interact over certain time points. But I do appreciate thinking that right now it could be valuable as well.
Thank you. Hope that answered Ali's comment. And then the next question from Renel Butlo. You can unmute yourself. Yeah.
Hi, Ken. It's a very great presentation.
Thank you.
So my question is the like whatever the results and the code transformation is available open source somewhere on the GitHub?
It's not open source right now. It's private GitHub, but I do intend to make the code base open source on GitHub. Yes.
Okay.
And
Thanks.
And like I said, there is a tool called Clairvoyance, if you wanted to research that, out of Cambridge, that does some very similar approaches. And that's what we use to validate and find an error in our code. So that is publicly available and that's out there. It's a tool you could use as well.
That's great. Thanks.
You're welcome.
so question from the chat. I think, let me go through. From Dr. Solman, are there any additional analytics or measurement from Teddy you would like to add to your model? If so, which are they?
Definitely. Like I said, I feel that there's the microbiome data we can look at where there may be immune response to from the microbiome that we can look at in combination with the proteomics. Also, I would like to look at the RNA-seq and the gene expression data. I mean, they're vast data sets, but I feel that they may provide even more insight into the pathogenesis of T1D, especially the prediction. And if that happens within the first 2 years of life, I think that would be a really good, insightful finding that the Teddy researchers could help me out with, because I really don't understand all of those various data sets. So I really appreciate the DCC and the Teddy PIs as far as being able to provide guidance with that.
Okay, and next question is from Dr. Talon. Approximately how many features are included in the current iteration of the RNN? Which features had the highest degree of missingness? Can you describe more about the type of interpolation you use to input missing data?
Sure. So the features, there were about over 300 that I reduced down to about 150. Some of those that were reduced were because they didn't meet the levels of detection. As far as the ones that were the highest on the model, I'm not sure if I can go into specifics of which ones those are, just because it's unpublished data. But I mean, I use proteomics and SNPs and other dietary data that, you know, they were the highest, I would say, indicators, but I don't think I can go into the specifics of which ones those are. As far as interpolation, I use the linear interpolation on that, and there's other available interpolation methods that are just straight out of the scikit-learn package that you can do, like spatial and things like that. But I don't believe all of them work for multivariate data, so you have to be considerate of that as well, depending on your data sets, if they're multivariate or not.
Okay, so next question in the chat is from Dr. Obid. Thank you for the fantastic presentation. Which machine learning model did you use to generate the SHAP plot?
So I used a combination of bidirectional LSTM and also the MLPs. So the static data was in the multi-level perceptrons, and then the temporal data was in the bidirectional LSTM. In the LSTM, I recently applied encode and decode methods, which is like an autoencoder approach. And then in addition to that, I added an attention layer for that.
Thank you. And there is one question from chat. Do you have recommendation for clinical researchers or bench scientists about data sharing? If we want our data to be reused for AI study in the future, are there any special information needed when we share our data?
Oh, definitely. I mean, data dictionaries are vital. Also, transforming. I think if I can create a tool that will transform some of these data sets into three-dimensional data sets for individuals, that may make things a little more easier as well. But data dictionaries, and then I do feel that it's critical to have staff that are knowledgeable with the data. I feel like if I was just handed these data sets blindedly, it would be really difficult for me to understand what some of the variables are, even with the data dictionary. So I think a critical step there is to have staff that are available, if possible, to help understand the data